Hello, welcome back. Hope you're doing okay. I I'm going to finish 14.6 today. So I'll review briefly what we saw last time on the gradient vector, and then show you a short application of one of these properties. Um, so, all right. Okay, so gradient. So in gradients, I have a function f, let's say of n variables. So the gradient of f, let's say x bar is some point in the domain of f, and I'm assuming f is a nice function. So the gradient of f at x bar is the following vector. So you evaluate all the partial derivatives, del f, del x1, del f, del x2, right up to del f, del xn at the point x bar. So this is what we call the gradient of f at x bar. This lives in the domain of f, okay? This is important to, so for example, if f is a function of two variables, then the gradient at some point will be a vector with two components, right? So if the point x bar is here, then the vector, we usually locate this vector at the point we're interested in. This is the gradient of f at x bar. So the first property we saw tells you which direction the gradient is pointing in, and it is the following. So fundamental property number one is that the gradient it points in the direction of maximum rate of change. So that indicates the direction of the maximum rate of change of f at x bar. Okay, so this we saw is actually pretty easy to figure out. Okay, what is the value of this maximum rate of change? So that's the directional derivative, and the value of this rate of change is the length of the gradient. Okay. Okay. The second property we saw, which was a bit more involved to figure out, is that the gradient is perpendicular to the level sets. Okay, so the gradient of f at x bar is orthogonal to the level set of f containing x bar. Okay, so let's just take a look at this in oh, yes, sorry, this page. I have like tons of windows open, so I don't always see the the chat. Sorry about that. Are you good? I can go back. Yeah. Okay. So All right.
Excuse me, sir.
Yes.
I don't really understand the second property.
Okay. Let's let me try to illustrate it for 2 and 3 variables again, and I will I don't want to go through the proof again, but I can briefly try to give you the idea again. So, okay, so here's the an illustration of this. So let's say we have 2 variables. So f is a function of 2 variables. So you take some point x bar in the domain of f, right? So let's say x bar is here, okay? And what I want to look are the level curves. So I look at the level curves of f. So what are those? So you fix k, and you look at all the points in the domain such that the value of the function is that value k, right? So these are curves on which the function, if you restrict the function to such a curve, it's constant, okay? So maybe they would look like that, right? So and I'll do the one through x, like that, okay? So again, what you're looking at here is the domain of f, okay? And if you look at the value of the function on these curves, the function is constant, okay? So now you look at the gradient of f at this point. And it turns out that it'll be orthogonal to the level curve. Okay, so it'll be, let me just modify this a bit. Like that. Let's put x bar here. So the gradient will be perpendicular to the curve. Okay. So I'm not explaining why this is true, but this is what is the meaning of property 2 is this, okay, in 2 variables.
All right, thank you, sir.
Okay. So if you look at the gradient at any point, let's say here, then the gradient, I mean, it could be pointing towards the origin. We don't know with this example, but it'll certainly be perpendicular to the level curve, okay? And again, if you want to keep in mind a nice image, if you're on a mountain, right, and you look at the direction of maximum rate of change, you're looking towards the top of the mountain, if you're on a trail, right, and the trail, if it's flat, should be perpendicular to this direction, right? So if you want to have an image, I think this helps, okay? All right. Let's take a look now at 3 variables, okay? So for 3 variables, I have a function f, and its domain now will be contained in R3, okay? So I take some point x bar in the domain of f, which is, say, R3. So again, I'm not looking at the graph here. I'm looking at the domain of f. I take some point in the domain, and it sits in some level surface, right? So we have the level surfaces of f. You fix, let's say, some k, and you look at all the points x, y, z such that the value of the function is equal to that fixed value, like that. So for each different k, you get a different surface. So maybe the surface is something like this, right? And let's say we have a point x bar which sits on the surface. So again, if you look at the sphere, the value of the function on this sphere, if you restrict points on this sphere, the value of the function is always the same, okay? Now the gradient then will be, so the gradient of f at this point will be orthogonal to the level surface. Okay, so it would be pointing outwards, or maybe inwards, but okay. So, and it's the same for any dimension, but let's let, if you want to be able to visualize things, these are the two cases we'll be looking at. Okay, so by perpendicular, how we defined it is that basically if you look at all the curves on the surface that pass through this point, you look at their tangent vectors, this gradient vector is perpendicular to all of them at this point. Okay, so that's what we, but notice now that this will allow us to define, because I mean, we have an intuition of where the tangent plane to a surface is at a point, but this is the way you define it. So you have this vector, which would be the normal to the tangent plane. So if you think of a plane which is tangent to this surface like that, so notice gradient of f at x bar is normal to the intuitive tangent plane to the surface at x bar. Okay, so that's the idea. So, but in fact, that's the definition. We're going to define the tangent plane to a surface this way. Okay, so that's the next thing I want to do, and the last thing in 14.6. Okay, so now we define tangent plane, and in fact, we're not going to go there, but you can define the notion of tangent space to any surface exactly in this way. It's the same definition. Okay, so that's what I want to do. All right. Okay, so let me remind you about surfaces, right? I have a surface, a two-dimensional surface that lives in R3. This would be described by an equation in XYZ, right? So describe okay. And we saw, so if you think about it, if you have an equation involving X, Y, and Z, you put everything on one side equals to 0. So basically the surface is given by an equation of the form f of x, y, z equals to 0, right? But what is that? That's a level surface of a function. So this is right? And so what we just saw applies in this case. So we know that the gradient of this function f at x bar is orthogonal to s at x bar, right? So this allows us to define the tangent plane using this vector. Now, there's something that I didn't mention in the last few minutes. I should have. We're assuming here that the gradient is not 0. So if the gradient collapses to 0, then none of this works, right? So note, provided the gradient of f at x bar is not 0. Okay, so this is like a bad case. black hole, okay? So you have a place where the gradient goes to 0, that's not good, okay? All right, so definition, we have a given a surface S, and I'll write it fully here. Sorry. So S is the set of all points x, y, z such that f of x, y, z equals to 0. And a point, let's say, x0, y0, z0 in S, right? So yeah, I'm going to give you an example in just 1 minute, 30 seconds. Okay. So if I'm given a surface S, which is a level surface, and I take a point in S, then the tangent plane or the plane, I should say, the plane tangent to S, the plane tangent to S at this point is the plane through this point, obviously, with normal gradient of F. Gradient of F at this point, provided it is not 0. Otherwise, this doesn't make sense. Okay, so that's how we define the tangent plane, which intuitively should be natural. Okay, so let's do an example. And this is very powerful, right? Because you can have some very, very complicated surfaces, but it's pretty easy to compute the tangent plane. Okay. Okay, so here's an example. So find an equation for the tangent plane for the surface. So here's the surface. It is x cubed plus y cubed plus z cubed equals 1 minus 6xyz at the point 0 minus 1, 2 to the power of 1/3. Okay? All right, so first, what you want to do is rewrite your equation as a level surface. Okay, so rewrite. So I'll rewrite it this way: x cubed plus y cubed plus z cubed minus 1 plus 6xyz equals to 0. Okay, so this is the function big F. Okay, so surface is a level surface of big F. Okay, and so the tangent plane, all I have to do is to find the gradient at the point I'm asked. That's it. Right? So we compute the gradient of F at the point 0 minus 1 to the power 1/3. So what's the gradient again? Gradient at any point, del F del X, del F del Y, del F del Z, like that. So I compute my partial derivatives. Let's see what we get. So with respect to X, I get 3x squared plus 6yz. With respect to y, 3y squared plus 6xz. And with respect to z, 3z squared plus 6xy. This is the gradient at any point. And if I evaluate it at the point 0, minus 1, 2 to the power 1/3, here's what I get. Minus 6 times 2 to the 1/3. This is 3. And this is 3 times 2 to the 2/3. If I didn't mess up, that should be it. Okay, so that's the gradient at the point we're interested in, and that will be the normal of our plane. So this is normal for our plane. You see it's not 0, so everything is great. Okay. So again, we haven't done this in a few weeks, so I just remind you very briefly, once you have the normal and a point, how do you find the plane, right? So I'm just gonna copy this. Okay, so this is our gradient, our point, x0, y0, z0, I'll call it like that, is 0 minus 1 to the 1/3, right? And so I want the plane with normal n through the point B0, right? In general, how does this work? If you don't remember, you can always work it out. So you have this plane like that. You have P0 like that. You have the normal sticking out, right? And you want to describe every point in the plane. So if you take any point, x, y, z, like that, sorry. Hello? Sorry about that. So if you want to describe every point in the plane, how do you figure it out? Well, if you take the vector P0 to this xyz, it has to be perpendicular to normal. In other words, the dot product is 0, right? So what you do is, it means that n dot x minus x0, I'm flipping the, no, actually I'm not, this is the same way. X minus x0, y minus y0, z minus z0 is 0. So this is your equation, right? So in our case, we're going to get, so n is my gradient vector, so this is minus 6 times 2 to the 1/3, 3 times 2 to the 2/3, dot x minus 0, y minus 1, and z minus 2 to the 1/3, which should be 0. So I just do the dot product, and so I'm going to get minus 6 times 2 to the 1/3 times x minus 0. I'll keep the minus 0 so you see the structure, plus 3 times y plus 1, plus 3 times 2 to the 2/3 times z minus 2 to the 1/3 equals to 0. If I didn't make a stupid mistake, that should be right. Yeah. Okay. Does that make sense? I have my headphone hair on today. Any questions, comments? Everybody's good? All good. Excellent. Thank you, Gabriel. So there is somebody out there. That's good. Okay, so this is the end of 14.6. Next week, I will start chapter 15, integration. Things are going pretty good, I think, hopefully, for you guys. Again, if you have questions, comments, please don't hesitate. You have a WebWorks open right now. So that's pretty much it for now. So unless there are questions or comments, that'll be it for today.